Welcome to everybody. So to this new seminar of the DinAmicI session. So today we have a special guest. We have Umberto Zannier from Scuola Normale Superiore in Pisa, and he will talk about his recent work on torsion in elliptic families, elliptical billiards, and diophantine problems in dynamics. Please, Umberto.
Thank you very much for the invitation. It's a pleasure to speak in your seminar. As the title says, I will illustrate some application to elliptical billiards of certain results which I will now recall. And I and my collaborators do not work in elliptical billiards, so we are rather outside the topic, but we noticed this possibility of application. So we went ahead in developing this. So I will start with a small review of, a very small review of elliptic curves. So just to remind anybody in the audience. So any elliptic curve, I will only consider elliptic curves over the complex numbers. And each of them be realized as a plane cubic that you may see written. I have written the affine cubic in the affine plane, but one should keep in mind that there is a further point in the projective plane to be added, which has the coordinates 0, 1, 0, homogeneous. And this equation defines a curve as soon as the polynomial, the cubic polynomial on the right, has no multiple roots. And A, B, C are complex numbers. The main point for us is that group law. So this curve, each of these curves has a group law, commutative, which may be explained geometrically and is known as the chord and tangent process, apparently first observed by Newton. The principle is that given 2 points, P and Q, you take the line joining them. Since we have a cubic, this line will intersect the curve in a third point. Everything is to be counted with multiplicity in case some of the points coincide. And you reflect this point with respect to the x-axis, and you obtain the sum. So this is important. It is expressible rationally. So you do only rational operations in terms of the coordinates. So it is an algebraic group law. In fact, it derives from the addition on the complex number if one views the elliptic curve as a torus, but let us forget about this. So we have this commutative group law. The history, these elliptic curves have something to do, they are not ellipses, but they arose from the problem of calculating the arc length in ellipses. And there is a relation also to elliptical billiards that I will recall later. So for us, the most important will be the torsion points in the curve. They are torsion with respect to the group. So an element of a group is called torsion if a multiple of the element is the origin of the group. So, and the analogy here to be kept in mind is with roots of unity in the group of non-zero complex numbers. They are the torsion points with respect to the multiplicative algebraic group. And here we have an analog torsion points on elliptic curves. As an example, the torsion points of order 2, so those points whose double makes the origin, are just obtained as the intersection of the curve with the x-axis. This is easy to check using the above geometrical description. The arithmetic of this torsion point is very deep and may be seen as a difficult analog of Gauss' theory of cyclotomy, which is already was very deep, especially in the times of Gauss, but still it is far from trivial. So we shall meet actually not rather than individual elliptic curves, so we shall work with algebraic families of elliptic curves. And I will work for the whole talk with the best known elliptic family, which is the Legendres elliptic family. What does it mean? Well, we have the equation, you see it in yellow. Y square is equal to a cubic polynomial, and in this family, the cubic polynomial has always the roots 0 and 1, and then a third root called lambda. And for each lambda, different from 0 and 1, we obtain an elliptic curve. So for varying lambda, we obtain this Legendres family of elliptic curves. Of course, I have again written only the affine equation. One should keep in mind there is the point at infinity to be added to obtain an elliptic curve. This lambda varies in the so-called base. The base is the space of parameters for the family. In this case, in our case, this base equals the projective line to which we have removed infinity and also 0 and 1 to avoid multiple roots. But the base in general can be taken also a finite cover of this of the line. So to allow that certain algebraic functions are well defined. Everything will be easy, and I will show example. So we may also think another viewpoint to see this Legendres family. One may view lambda as being a variable, and then the equation defines an elliptic curve over the field of rational functions with complex coefficients. So one may view also the family as a single elliptic curve, however, where the coefficients now are not numbers, but are rational functions. This viewpoint is often useful. So I have pictured this picture. You see, we have the base B, the parameter space, and for each point on the base, we have a curve. And this curve appears as the fiber of this function pi. The function pi is a function on the total space and sends each point to the base. So the fibers of pi are the elliptic curves in the family. An important remark is that there is no group law on the total space. There is a group law on each fiber. We cannot add 2 points which belong to different fibers in general. Sections. So this is practically the last definition that I give, but it is important, very easy, but important. Sections of an elliptic family. A section is simply a map which assigns from the base to the total space. You see it's sigma from B to L. And this function must assign to a point of the base 1 point in the elliptic curve corresponding to the point in the base. So you may have a section, and the image of the section is like the graph of a function. And this section may also be seen as a point in the generic fiber of the family. Let me give simple examples. We have the zero section. So, as I said at the start, each elliptic curve has an origin, which is represented by the point 0 1, 0 in the projective plane. The point at infinity plays the role of the origin for the group law. And the 0 section is the one which assigns to each point of the base the origin. So, but we may view this point, we must view this point as a point of the curve L lambda. So this is more precise rather than seeing this point as a point of the projective plane. We must see it, think as a point of the fiber curve. And then other is called section, I call it because Masser used this section to formulate some of the problems which will be relevant here. This section is obtained, you see the abscissa is constant, equal to 2, and the ordinate is just obtained by putting x equal to 2 in the equation for the Legendre family, and then we obtain y just by solving the equation. So y is the square root of 2 times 2 minus lambda. So we obtain, you see, for each value of lambda, we obtain a point in the curve corresponding to lambda. In fact, there is a slight abuse of language here because we have not specified the sign of the square root. And this will be material for us, but just to be precise, let me say once and all, the base here is not the lambda line, but a quadratic cover of the lambda line. This is the first time you see that we have to take a cover of the base to be able to choose the sign unambiguously. Otherwise, we have a multi-valued function. But you may forget safely about this. So, torsion set of a section. So, a section assigns to each point of the base a point in the elliptic curve above the point of the base. Here is the picture. And this point may or may not be torsion in that curve. So the torsion set of the section is the set of points of the base where the value is a torsion point. You have an analogy here, easy, that I have not written, but I can say in words. If you have a rational function, for instance, think of a rational function, you may view it as a section for the multiplicative group, and the points where the rational function assume a value which is a root of unity would be the torsion set of the rational function in the case of the multiplicative group. So this is an analogy, perfect analogy in the elliptic case. We take the points of the base where the value of the section is torsion. And this set was investigated for many reasons. For instance, when a point is not torsion, you take the multiples of the point, and if this point is a rational point, for instance, you obtain infinitely many rational points on the same elliptic curve. Whereas if the point is torsion, you obtain only finitely many multiples. So one motivation to consider this torsion set was to obtain infinitely many rational points in elliptic curves. And so one had to narrow, for instance, the points where the section becomes torsion. And there are two basic cases to study when we are interested in this torsion set. The first case, which I call trivial case, occurs when sigma is identically torsion. Namely, it is torsion on considering lambda as variable. This means that for some fixed integer n greater than 0, n times the section is the 0 section. Here is the simplest possible example, apart from the 0 section itself. you see, if we take the section with the abscissas lambda on the Legendre curve, if you put x equal lambda, you obtain y equals 0. So we have the section which assigns to each lambda the pair lambda 0, which lies on L lambda. And as I illustrated at the beginning, the points where the y coordinate is 0 are of order 2 for the group law. So their double is 0. And so we have here an example of a section which produces constantly a torsion element. In this that I feel, we have that the set of the torsion set is obviously the whole base, because the section is identically torsion. So whichever value we take, we obtain a torsion point. So we obtain the whole base. So from this viewpoint, this is a trivial case. As I wrote here, still there are some non-trivial issues in this trivial case. For instance, if we are given a section, how to prove that it is torsion or non-torsion? This is not an entirely trivial issue, but I skipped this for today's talk. And a remark is that, for instance, Masser's section, it is written here, may be proved to be non-torsion. It is not identical. You see, to check that something is non-torsion, in principle, we have to compute infinitely many multiples. So we must use some other method to exclude that the point is torsion. But in the case of the Masser section, it may be proved easily if one knows a little bit of general theory. But I skipped this. Believe me, Masser section may be proved to be non-torsion. Now let us go to the non-trivial case. So in the sense, non-trivial in the sense that the section is not itself identically torsion. And then what can be said on the torsion set? So the section is not identically, does not produce identically torsion points, but still the torsion set could be very large. Let us recall what can be said. On the one hand, it may be proved that this set is in a certain sense small. What does it mean small? In this case, for instance, it may be proved that if we work over the algebraic numbers, as in the case of Masser section, for instance, one may prove that the torsion set contains only finitely many points of bounded degree over Q. So, for instance, we have Masser's section. If we take a lambda as a rational number, this all number torsion and lambda not but a quadratic irrational, again only finitely many quadratic irrationals independently of the field. So there are only finitely many quadratic irrationals such that P of lambda is torsion. So this is a measure of that the set is not so large, because we have finiteness as soon as we prescribe some bound on the degree. But on the other hand, this set is not too small, so is in a certain other sense large. For instance, it may be proved that it is dense in the complex topology. So an apparently strange thing happens, that for a dense set of complex number, we obtain a torsion point, but the complement is very large. And actually only finitely many of points of this dense set may be rational or quadratic irrational and so on. I skip here many other things that can be said, due to work of the authors that you may see written: Manin, Silverman Tate, Masser, DeMarco Mavraki, Corvaya, Habegger, Brian Lawrence, Julian De Maio, and others. Now let me go to the case of two sections. Suppose we have a second section. I write just this section for simplicity. So you see now I have again taken the Legendre curve. I put now the abscissa is not anymore constant. It is equal to lambda plus 1. And again, the ordinate is obtained just by solving the equation of the Legendre elliptic curve. Again, there is an ambiguity on the sign, but let us forget about this. So Masser posed some questions several years ago, and he wondered, so each section has a torsion set. Each torsion set is infinite, but in another sense small. He asked what can be said about the intersection of the torsion set. So the lambdas which produce torsion both for the first section and the second. And after this, we succeeded in proving that there is finiteness. So if we impose a single torsion condition, we find a small set, but not too small, in fact, a dense set. But if we impose a double torsion condition, then we have finiteness. Independently of the degree, we have many lines such that both P and Q are torsion. And I have just taken two special sections for the sake of example, but this type of result holds generally. So for each pair of sections, but not for each, but for each pair of sections which are linearly independent on the curve. There is a condition, a natural and necessary condition on the pair of sections. If the sections, you may imagine, if the sections are linearly dependent with respect to the group law, then being torsion for the first one implies torsion for the second one and conversely. So taking the intersection gives nothing, does not restrict. So when the sections are dependent, intersection is still infinite, but if they are independent, then it is finite. And there are even more general results, or may extend to several sections, or also to families of abelian varieties, more general than elliptic curves, with similar finiteness conclusions. I do not state for simplicity any precise technical statement, but just say that if we tenuous torsion, we have finiteness if the sections are linearly independent, if we consider the same elliptic curve, or generally if they do not map in a so-called subgroup family. And this result that I have vaguely stated may be viewed as an analog of what was called the Manin-Mumford conjecture. This Manin-Mumford conjecture, which was solved in the 80s, for torsion points in subvarieties of abelian varieties with certain conditions. And the difference here is that in the Manin-Mumford conjecture, the ambient abelian variety was fixed, whereas in these theorems, we have a family. So we have something varying. So the proof methods for the Manin-Mumford conjecture had to be changed because they didn't work for for spaces which were varying. And Baroero Capuano treated also arbitrary families, intersecting they consider not just the torsion, but they consider subgroup families. of codimension at least 2, and they proved the theorems which gave the previous one as special cases. And these other authors, Gio Garcia and Tucker, had done before some special cases. Now let me come to the applications to billiards. And billiards, for me, I will consider only elliptical billiards. So elliptical billiards are billiards, of course, whose table has a border which is an ellipse. And the law is the usual reflection. So we obtain a billiard trajectory. And an old theorem, which but very interesting, which may be proved by Euclidean geometry. It is not a stupid theorem, it is subtle, but it may be proved by basics of Euclidean geometry. And it's that take a billiard trajectory inside an elliptical billiards, inside a fixed elliptical billiard, all the segments in the trajectory are tangent to the same confocal conic, and this is called the caustic. It may be an ellipse, like in the picture, or also a hyperbola. So to each billiard trajectory is associated a caustic. Here I have written equations, for instance, for the ellipse, x squared plus y squared over 1 minus c squared equal 1. And c here is another equation for the family of caustics. This depends on the parameter that I called S. So now let me illustrate the relation between the elliptical billiards. So the trajectory is tangent to the caustic. And then let us look at the tangents to a caustic. The tangents to a given caustics may be seen as points in the dual conic, the caustic dual conic, which consists of the tangents to the conic itself. And these tangents are viewed as points under the duality of the projective plane, the simple duality. So a billiard shot, we may view a billiard shot as a pair consisting of a point in the border and then a line which is tangent to the caustic. So we have a pair, and the pair is inside the product of the curve times the dual. For a given S, so if we fix the caustic, these pairs form a curve. And this curve is generically of genus 1. This may be proved, it requires proof, but it is not difficult. And so this pair may be viewed as an elliptic curve. We may consider the Jacobian, but if you want to avoid any technicality, we have the set of pairs which this set of pairs such that the point lies on the line. So we have the product of the ellipse times the dual conic. This product is a set of pairs, but only for some pairs the point belongs to the line. And the set of these pairs form a curve which is of genus 1 and may become an elliptic curve as soon as we choose an origin. So let us think we have chosen an which varies with S, and we obtain an elliptic curve. So we have an elliptic family, because to each S we may associate there is a caustic which depends on S, and once we have the caustic, we have this curve which is an elliptic curve. So we have an elliptic family depending on S. Algebraic family of elliptic curve, and this algebraic family is parameterized by the space of caustics. And here we have the billiard map. The billiard map associates to the point, the pair in yellow, PL, the other point in red, which consists of the pair corresponding to the next segment in the trajectory. So this billiard map sends the curve, sends the curve into itself, and a theorem of Poncelet and Jacobi says that this billiard map is a translation in the elliptic curve. So with respect to the group law of the elliptic curve, it simply translates. And this depends only on the caustic. It does not depend on the initial point. This was discovered by Poncelet. And then Jacobi gave a proof based on elliptic curves. Poncelet actually argued more generally, not only with an elliptical billiard, but with arbitrary pairs of conics. But I skipped this for lack of time. So what this the corollary of this theorem says that the trajectory is periodic and only translation. And this does not depend on P, on the initial point. It depends only on the caustic. If we perform a billiard trajectory into the same caustic, but with a different starting point, we have periodicity if and only if this happens for a single point, and then it happens for all. So this map beta, another thing that we may say, may be seen as a section of our elliptic family, because to each member of the elliptic family we associate this translation, which is a point in the elliptic curve. Let me go to illustrate some billiard games. So we have a point, for instance, we choose P naught in the border. For instance, just for the sake of example, point with the abscissa -1, ordinate 0. And then we have a slope, psi, which is the direction, the slope of our first shot. And then we have this simple formula which associates to the slope. It associates the parameter S corresponding to the caustic. It may be computed as this, with this formula. And we may put this in Legendre form. And the Legendre parameter is given by S divided by C squared. And there is a theorem, very easy, that the section provided by the billiard map is not identically torsion. This is very easy by continuity. I skip the argument. By using the Heron-Fermat principle, one may prove that there are trajectories periodic of any given order. Whereas if the trajectory is non-periodic, then it will be dense in the shaded region, which is included, you see, between the ellipse and the caustic. In the picture, we have a hyperbolic caustic this time. The slopes of periodic trajectories correspond to the torsion set that we have considered before. So this becomes relevant in the theory of billiards, because to my knowledge, in the theory of billiards, one is often interested in periodic trajectories, of course. And corresponding to this link between elliptic families and billiards, let me state some finiteness results in elliptical billiards. I start with an example with two players. Suppose the two players make these strange games, which is rather unrealistic, but we may imagine this game. So they start the two billiard shots, starting at the same point for simplicity, P naught. which is the point -1, 0 on the ellipse. And the rule is that the difference, the angle between the two directions is fixed. So we may pick an angle between 0 and π², for instance. We fix the angle in advance, and then we consider pairs of shots, of billiard shots, such that the direction differ by this angle. And we may ask, how often will both trajectories be periodic? If we just look at a single trajectory, then we shall obtain periodicity for an infinity of directions. But if we prescribe the periodicity for both, we may prove that we may obtain only finitely many times. And this I will sketch the proof. So, but I make a remark that for usual rectangular billiards, this result is not always true. It may be proved to be true for non-CM lattice billiards, but not generally. And McMullen showed me a property that makes it probably true also for polygonal billiards with more than 4 sides. But this has not been written down. I consider it curiosity to check for which types of billiards such an assertion may be true. So to impose 2 periodicities at the same time. So proof, a sketch of proof. We have 2 sections. Now, the sections, what do they do, these sections? We view the elliptic family as depending on the slope. So the slope is our parameter. And associated to a slope, we have the translation predicted by the theorem of Poncelet-Jacobi. And but now we have 2 slopes because we have the slope of the first player and the slope of the second player. And so we have 2 sections. And none of the section is torsion because they are both billiard sections. So we can apply the result that I have stated before, joint with Masser. We have finiteness only if the image of the section pair is not contained in a subgroup family. This corresponds to check independence. But now we have practically two elliptic families corresponding to the 2 sections. And it suffices to show that the families are not isogynous. This means that there are no non-trivial generic algebraic maps between the 2 elliptic curves in the families. And if this is the case, it follows from general theory that there are only trivial subgroup families. So the condition to apply the theorem with Masser is automatically verified. So to prove the theorem, we have to prove that the families are not isogynous. And how to prove this? Well, we have the Legendre parameters. The Legendre parameter is given by the formula that you see written. Lambda equals psi squared plus c squared over psi squared plus 1. This is the Legendre parameter corresponding to the slope psi. And now we have 2 slopes, psi1 and psi2, and they are related by the formula that you see written. This formula corresponds to the fact that the angle between the 2 shots, the 2 directions, is fixed equal to alpha. So the usual formula for the addition of tangents gives the formula for psi2. So we have 2 Legendre parameters depending on the same slope. And how to check that the families are not isogynous? Well, I skip this. One may use the so-called modular equations. For lack of time, I skip this technicality. it may be checked by using the properties of the so-called modular equations. These modular equations form a family. There is one modular equation for each integer, and they classify the isogenies, so to say, and looking at the poles of the functions, one may exclude that any of these modular equations is verified. So this completes the sketch of the proof. Another example of application is obtained if we have a billiard with a hole. Now we have two balls, A and B, and the hole H. And we want to hit the second ball with the first, so that the second ball goes eventually to the hole. And of course, in principle, we may do this in several ways. For instance, we may hit directly the second ball with the first, or we may first go, we may hit it after a certain number of rebounds. And the problem to describe all the possibilities that send the second ball eventually to the hole. Are they infinitely many or not? This is the main question that one may ask. A priori, they could be infinitely many. Here we have shown of our elliptic family corresponding to the slope of the first shot. And the winning shot must obey two conditions. For some integer m, we reach the point B after m rebounds. And then once we have reached the point B, we have a second condition. For some integer n, the shot from B goes to the hole n rebounds. So we have two integer variables that measure the number of count the number of rebounds. So let us formulate this condition in terms of the billiard map, and you may see it, the two displayed equations. We obtain, I skip the details again, but it is just a matter of translating the formulation of the problem into the picture that I have given for the elliptical billiard, and we obtain, corresponding to the point, to the ball B and the hole H, we obtain two sections. There are two sections, and we have the billiard map, and you see we have two equations for the billiard map, which have to be verified for a same value of the slope. So this again says that it is unlikely that we have infinitely many shots because we have only one variable, but this must be proved. And indeed, it may be proved by using the above theorems, provided, however, that the balls do not lie in the foci of the ellipse. Otherwise, it is false. So this theorem requires the application not merely of the results with Masser, but either of the result by Gio, Garcia, and Tucker, or the generalization by Baruero Capuano. So this is the theorem with Corvai. There are only finitely many slopes, sending A eventually to B and eventually to H, unless A, B are the foci, in which case every slope sends A to B, and for an infinity of them, they go to H. The proof of these theorems correspond, again, I have no time to illustrate why, but correspond to finding, so the solutions of these conditions are like rational points on analytic curves. So we have a torus, think of a torus. For instance, the standard torus obtained on dividing the complex plane by the standard integral lattice. And think of a curve, of an analytic curve going through the torus. And the problems that I have formulated correspond to ask whether this analytic curve contains infinitely many rational points in the torus. So it is a problem of diophantine type because you want rational points on a curve, on a real curve in this case. But the curve is not an algebraic curve. So this is the difference between this context and the usual diophantine context where you ask for the rational points on an algebraic curve. Here, these curves may be obtained, but they are only analytic. And still, one may prove in these cases finiteness for the number of rational points on these analytic curves. So now my time is almost over. So I will go to the end. I skip the further example, which concerns boomerang shots in the billiard. So we want to shot such that the ball passes again through the initial point more than once. I skip this. And but I want to remark that the problem that I have discussed, especially the second problem with the hole, corresponds to this problem that I have stated in the rectangle. Given a surface, suppose we have a real surface, an algebraic surface, or generally a surface with an endomorphism, beta. And then we have three curves on the surface. And we are interested in the set of points in the first curve, such that for some iterate of the endomorphism, the point goes to the second curve and then on the third. So this is a problem, general problem in dynamics. It is in the spirit of the so-called Mordell-Lang dynamical conjecture, which has been studied by authors that I have written: Bell, Jason Bell, Gioca, Scanlon, Tucker, Shouvu Zheng, and others. But it is slightly different from that. So the problem that I have discussed before can be seen as a problem of this type, where the surface here will be the projective, the product of the ellipse by itself, and the beta corresponds to the billiard ball, an endomorphism of the square of the ellipse. But now that we have this general formulation of the problem, we may pick other special cases. So the first example is the one that we have seen. Another very simple special case is when we take the surface being the projective plane, the simplest surface that we may think about, projective plane, and the three curves are the simplest curves that we may think about, namely lines, and the endomorphism is the simplest possible, linear. And then the problem turns into an equation of exponential polynomial type between linear recurrent sequences. And this time, it requires deep tools to be studied, all relying on the so-called Schmidt subspace theorem, which is quite a deep theorem in diophantine approximation and diophantine equation. So I will stop here, but the conclusion is that the same general problem leads to quite different methods of proof and to quite different ambients, just by a small change. The example one, the surface is just an ellipse by itself, so essentially P1 square, and we have an endomorphism which corresponds to billiard map, and that leads us into the theory of rational points on analytic curves. Whereas the second example, which is again very simple, projective plane and the lines, leads us into the theory of ordinary polynomial exponential diophantine equations, which are treated by entirely different methods. So it may be of interest for me, at least, to see if there are other cases which may be dealt with the existing techniques. So I stop here and thank you very much.
Thank you, Umberto. I clap for everybody. So thank you for the very nice talk. So there is time for some questions or comments. If anybody has questions, please, in case, just unmute yourself and feel free to ask. So I start with one question. So are these result about, so I have two questions actually. So the first one probably stupid, but does this result on the finiteness remain true in the limit as the ellipse becomes a circle? And in case, what gets wrong in the proof if it's not the case?
Yeah, yes, the case of the circle is easier to study because yeah, it is a kind of degenerate situation, but it makes perfectly sense.
Okay, so also because I was thinking in the case of the circle, the angle is constant.
Yes, so, exactly. So certain things cannot be formulated equally well.
Okay.
For instance, the foci are there is only the center. So even the exception in the second theorem disappears. But I have not looked at the analogy, but you are perfectly right. One should look at it, and usually it is. Sometimes it is. The result is the same. Usually easier to prove, but it makes perfectly sense to specialize to the degenerate situation.
Because I was thinking, since theta is constant, as long as theta plus alpha is rational with respect to pi, you get a periodic orbit.
Exactly.
And so maybe it's not finite.
So it is not generally, you're right, that is another example, thank you. We shall point out this, where the finiteness conclusion fails, as it fails for some rectangular billiards.
Okay, and then another question, but this is more curiosity. So is it possible to rephrase this theory, assuming you have some billiard table with some general hypothesis that I don't know, meeting a family of caustics with some hypothesis, then your results follow? Because the ellipse is very special, but maybe you just need
this would be for me quite interesting. So, but I am not familiar with the general theory, and so I don't know. Okay. But I doubt that the methods of proof may continue to hold. So we remarked also this in a paper, that we don't know of analogies, but we doubt that the proofs continue to be valid, because the algebraic restriction is very important in the proofs. So even if the curves that I mentioned are analytic, they have special properties. And if we do not have some strong assumption, the finiteness results are actually not true.
Okay. Okay, I see there is a question by Stefano Marmi. So Stefano, unmute yourself.
Sì, first of all, ciao Umberto.
Thank you, Stefano.
No, thank you for the talk. It was very nice. Two minor questions. I mean, one was if you can elaborate a little bit. You made a comment about extending results to polygonal billiards. Can you say a little bit more about that? And the second one, can you say a few more words on what you said at the very end? So that in some cases you just end up by applying, I mean, the theory of linear recurrences and the Schmidt subspace theorem.
Yes, thank you for both questions. So in the case of the first, for rectangular billiards, it is an elementary argument, not completely short, not very short, but elementary. Which says that I want to find the so for rectangular billiards, I don't find. Oh, here it is. Yes. For usual rectangular billiards, the finiteness holds. So a rectangular billiard I represent with respect to a lattice, to actually a general lattice, parallelogram billiard. And if the lattice is a so-called complex multiplication lattice, so such that the quotient of C by this lattice corresponds to a curve with complex multiplication, or equivalently, if the lattice has non-trivial endomorphism, then the finiteness again does not hold. But it holds in all other cases. So it holds if and only if the lattice is non-CR. This may be checked by an elementary argument. And regarding your second question, yes, one may translate in the case of the projective plane and the three lines and the linear endomorphism. Then the point is the iterated of the linear is expressed by power of a matrix, a 3 by 3 matrix, up to scalars. And so the entries of this matrix become linear recurrent sequences evaluated at the n, at the parameter expressing the iteration. And if one formulates, it is easy to do a little consideration. We obtain the equation that you see displayed. It is an equation, multiplicative equation relating 4 recurrence sequences. And now there are 2 variables. And so even the usual Scuola-Mahler-Leck vanishing theorem for linear recurrent sequences is not enough. And the presence of a second variable requires deeper tools. And they have been developed by the authors that I have written down, Everts, Van der Porten-Schlickewey, Michel Laurent, and others. And all rely on the Schmidt subspace theorem, which is a far-reaching generalization of the theorem of Roth in diophantine approximation. For P, it was somewhat straightforward, very long to classify all possibilities. So I wonder what happens if one takes a higher dimensional example and trying to obtain some general condition, so which does not require this boring and unnatural distinction into cases.
Thank you.
Okay, so is there any other comment or question?
Thank you very much for a very interesting talk. So I would like to ask, so your result about finiteness in billiards states that for any individual alpha, the number of angles, of departure angles, for which both trajectories are periodic.
Can you repeat, please?
Sorry?
Can you, I couldn't hear well, excuse me, if you can repeat.
Okay, so my question is the following, so it concerns the theorem on elliptic billiards.
Yes.
Yes, so if you just take 2 departure angles with difference alpha, so then you're looking for those departures for which both trajectories will be periodic. And your result tells that for each alpha, there are only finitely many speeds for which it is will be periodic. So this is a finite number of initial speeds. Is this finite number bounded by some uniform constant independent on alpha?
Yes, this is interesting, and I think I cannot prove this. However, probably this is true, but such uniformity, we haven't been able to prove it. So it might be true, but the method gives a different bound. Actually, it is not even still effective to find write down whenever you know the angle, to write down the finitely many periodic trajectories. Now, very recently, Biniamini has obtained some effective and uniform versions of the theorems needed in the proof. So it may be that with these very recent results, one may give some kind of answer to your question. Yes, excuse me, I forgot to answer completely to the question of Stefano Marmi, who asked about polygonal billiards. I only said about the rectangular. McMullen told me about the property of periodic trajectories in other polygonal billiards, and this property make it likely that the theorem of finiteness remains true for polygonal billiards with more than four sides. But we haven't proved this. He just, during a similar talk, pointed out this property. And I don't know if, in fact, this property is sufficient to imply at once finiteness.
Okay, thank you.
Okay.
So, other comments or questions? So, otherwise, let us thank again Umberto for the very nice talk. I clap for everybody.
Thank you very much.